Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. I'm very glad to visit Microsoft, and thank you, Jin, for inviting me. So in today's talk, basically I will cover a couple of topics. One is straight from the paper that I will be talking in SIGCOMM, and it's a collaboration with PP Live that we did on their P2P VOD system. And then after that, I will try to give some, introduce some of the work that we have been doing. I think in academic world, people want to just study more modeling, the capacity of P2P networks, the algorithms, modeling, and so on. So I'll talk a little bit about that if there's time. Okay. So the case for P2P VOD, I think this has already been well established last year in the SIGCOMM conference, in fact, by people sitting here, that you wrote a good paper studying from the Microsoft VOD, client-server VOD system, and then analyze how you might use the P2P technology to significantly reduce the server loading. Okay, so you can make it more scalable. So you call it peer-assisted VOD. I think it's the same thing, P2P VOD, meaning the same thing. So the key challenges is clear. We already have P2P streaming systems for working, for quite a few years. I think that was started, originally from the cool streaming paper in Infocom several years ago. And since then, several platforms have been built, and so people already feel that P2P streaming is kind of mature. You know how to do it, and it can be done quite well. But for P2P VOD, it's a different story, because for P2P streaming, you have a lot of users. They are viewing the same content at the same time. So it's kind of intuitively, it's easy to make them kind of help each other, share the content they are watching. They have more or less the similar content in their buffer, and then can easily help each other by relieving the server in terms of serving each other. But for P2P VOD, this is a different story, because you can have all the peers, they may be viewing different movies. There can be many movies, and also even if they're viewing the same movie, it could be they're looking at different parts of the movie, and how to make them help each other is a much more challenging problem. So so how to build a system, whether it can be built. I mean, I think the paper last year was more a sort of paper study, and you sort of describe how you might use prefetching to essentially for the peers to fetch the content, and then under optimal situations, you can cut down the server load to around 10%. So I think you predicted that through the analysis. So the question is how to build a system that will actually deliver that. I think apparently while you were working on that paper, the people in the doing P2P streaming, they already started doing these kind of systems. And I think in the case of PP Live, they built a kind of system in maybe last summer, and they were testing it. And then by last fall, they deployed the system. And it reached the scale of several, hundreds, thousands of subscribers and many thousands simultaneous users. I think over the I don't want to give exact numbers because I don't know necessarily exactly what's the scale, but I think these are the kind of scale that was reached.
I mean,
Yeah.
I noticed this number is much smaller than their live streaming number.
Yes.
I mean, but actually, I think VOD is a very popular form of service.
Right.
I notice for my personal habit, once the VOD is here,
Right.
I use that option. Why?
Right.
I mean, the number of subscribers is much
Okay, so I think part of the reason is when they first started the deployment, I think they were trying to be cautious. They were using a low-profile way of starting it. They just created some button on their streaming thing, and then so some people may not notice there's such service. And partly, I also think some of these things I'm just conjecturing, okay, because our collaboration with PP Live is I was not there, sort of running their system, so neither was I sort of involved in building the system. But mainly we were trying to sort of working with them, trying to bring out the insights of the design of the system, and also through the measurement, study some of the user behavior and some of the sort of how to measure the system in order to make sure it works well. So to answer your question, I think they were my conjecture is they probably try to be cautious because P2P VOD actually does take a lot more server load. Okay, so if they are, trying to go very fast, I mean the performance may not be so good. Okay, and then the other thing they can control is in P2P VOD you can sort of control the server loading and how well you do by limiting the number of movies. If you reduce the number of movies to only the popular ones, you can probably reduce the load initially, and then that you may lose some users if you have only a few popular movies, not so many movies. So they were going through I think a period to build up. I mean this. I think it's not surprising that compared to their P2P streaming, their P2P streaming is very mature. In fact, the numbers is for P2P streaming, they can the server loading is at probably 1% or less. I mean, the server doesn't need to do much. But for P2P VOD, initially when they deployed this, as I will mention later on, the server loading was 20 to 30% of the of compared to whether the server would serve by itself. Yeah. And then eventually, only this year, I think, earlier this year, they cut it down to about 10% level. Okay. So so they are still going through this. I mean, I think they're still trying to optimize and make it work better. But I think what happened is they actually did succeed in demonstrating a relatively large-scale system can be built and made to work. Okay, so and also that through the measurement we can see that in fact the system delivers reasonable user satisfaction, and we'll look at how to measure that. And obviously they also do some subjective kind of measurement by having friendly users look at the video and see whether it's delivering reasonable quality. So this is just a little animation to show that the point I made earlier, that for streaming you have essentially all the users looking synchronized. They're looking at more or less the same video at the same time, whereas for P2P VOD you can have different users looking at different movies or different parts of a movie. So that's why the problem is more challenging. So what is the secret in their system? I think the probably the most I don't know whether this is how everyone builds it, but the way they make it work is to, in addition to making all the peers share what is sitting in their buffer in memory, they also make the peers contribute some storage. Okay, this is a significant difference than the P2P streaming. So as you watch movies, you would be, after you watch it, you would just leave some of the movie in your storage. And when you're online, you may be watching one movie, but if there's another user who wants to watch some movie which is sitting in your storage, you can also serve that user. So that is how they manage to make the P2P VOD work. So each user, each peer is contributing about 1 gigabyte of hard disk. So the key problem of P2P VOD is how to manage this storage so that the users are leaving the right content in their hard disk. So when the other users come online, there's sufficient content out there sitting in different peers' hard disks who are online, and they can relieve the video server. Okay, so that's the challenging problem. So this is new. This is an addition to whatever you have to do with in P2P streaming already. So some of the other things I observe, which is I think in building this system that in contrast to the file sharing protocols like BT and so on, in this system that PP Live built, it's really more like a distributed system. They're not letting the peers sort of control so many things. It's in fact, if a peer wants to watch their the system, they have to watch the movie. They have to stay online. They have to essentially contribute. Okay, if they don't contribute, they have to show that they are still connected through heartbeat messages and so on. If they are not contributing, they're not watching. They cannot watch. Okay, so this I think also solves the problem of free riding. I think there are many other less technical factors that are important to make such a system successful. For example, working with ISPs. I know they work quite closely with ISPs. In fact, the ISPs are happy to have them help them provide some content in many situations, and then they actually work closely with ISPs. Obviously, you need to get good content to draw the eyeballs and get commercials and these kind of things, which I think are more important. I mean, are very important for the success of such systems. So the problem we're looking at is really a problem of how to do content replication, right? So what they are doing is what is known as multiple video replication. So in traditional P2P streaming, essentially everyone is watching the same thing. So there's only one video, okay, you're concerned with. There's a tracker that keeps track of all the peers watching that video and so on. So in their system, essentially each peer is storing multiple movies. So the tracker system has to know given a movie, which peers are storing that movie and can provide help. So you need to build a tracker system to provide information at that level. And then you also need to make sure that the I/O system is fast enough in bringing the movie into the memory when you need to serve other peers. So the replication of content is at two levels. One is at the movie level. You need to you provide multiple movies, serve other peers, and also at the chunk level. So once you have a movie, you are sort of serving another peer. You store what chunks you have for that movie into a bitmap. This is just like traditional P2P streaming. There's no big secret there. In their case, the size of a chunk is about 2 megabits. So to store a movie, it's at the resolution that they have, it's about 100 bits of a bitmap. So here's okay.
tracker know which chunks the node which node has? Or does the tracker only know that this node has something about this view?
That's a good question. Actually, later on I'll clarify on this point, because the tracker actually does keep track of all the chunks, what chunks peers have. And in fact, let's see. Now the tracker keeps track of which chunk. I know the. Sorry, I know that the tracker keeps track of which chunks it has, but I forgot why it has to do that. But in terms of streaming, mainly you find out which chunk, your peers have through gossiping. Okay, that's because it's more up to date. Okay, but the tracker does keep a lot of statistics. So you have the movie is divided into different pieces. You have what is called a chunk, which is a bigger piece, about 2 megabits, and this is used to advertise. This is advertised in the bitmap. So you exchange this information with your neighbors, and then you have what is called a piece, which is a minimum viewing unit, which is about 16 kilobits. And then you have a sub-piece, which is about one kilobyte or bits. I'm not sure, but this is more used for transmission. Okay, 1 kilobytes, I think. So you need to schedule the transmission and from different neighbors. So I mentioned this point later on in the algorithms. So there are 3 important algorithms. One is piece selection algorithm, which is this is the streaming part. You have to work with different neighbors to find out what piece to get from other neighbors. The other one is the replication algorithm, which is what I mentioned earlier. This is the important new aspect of P2P VOD, is to decide what movies you will store in your hard disk or keep in your hard disk. This is like managing the cache. Okay, and this one, in order to do this, the tracker collects information from different peers, and then give peer the information called essentially supply to demand ratio. It tells you which movies are in supply and which movies are in demand. And given this information, you can decide better, which movie to store. Okay. The third algorithm that's very important is the transmission scheduling algorithm. So in their system, what they do is each peer, when they try to get a chunk from other peers, they actually try to get it from different peers. Okay, and then they need to schedule how much to request each neighbor, and to achieve the load balancing. So this is actually a very tricky algorithm. If you don't do it right, you will not be making good use of the uplink of your neighbors. So these 3 algorithms actually, I think they are all interesting algorithms worthy of further study in terms of research. In their system, they just build something ad hoc. I mean, they just try different ways of doing it and see how well it works. In terms of piece selection, this part is kind of similar to P2P streaming. We all know that essentially there are 2 kind of algorithms for pooling data. One is, by the way, their system is more or less a sort of a mesh-based system. Okay, not a tree-based system. So the peers basically pool the content from neighbors. One approach is called a sequential pooling, so that you try to get, you're a little bit short-sighted. You try to get what you need to play back, so that the most urgent content have higher priority. You get that first. The other approach, the other algorithm is called the rarest first. This one, the name comes from the BitTorrent, and essentially you're trying to get the freshest content first. That whatever the server is sending out, and you try to get that first. And this strategy helps propagate the content as to provide the scalability. So this one, this is the other one, and a third algorithm is called anchor-based, which is you try to select certain anchor points in your video, and then randomly pick an anchor point and then do sequential from that anchor point. This also helps. This achieves two things. One is to, if certain anchor point which are, viewed more often, people tend to drag, to that anchor, to that, to certain area. Then you can use the anchor point to approximate. Essentially, the user try to move their viewing to a certain point. Okay, and then if you cannot exactly move to that point, you can at least move to an anchor point close to that, and so sort of like a little bit cheating way of simulating the moving to random moving. And another thing that anchor point helps you is that it also is a way to help different peers to sort of collect different things so that they can help each other. Okay, so that's also how anchor point can be used. So in PP Live's system, they actually use a mixture of this. Later on, I think in fact they experimented with the anchor point approach, and they found that at least in the current deployed system, they don't need to use that because the users are not essentially moving, jumping too much. Okay, you will see from the measurement data that is the case. So the second class of algorithms that's very important in the overall system design is the replication algorithm. In their system, they are not doing any prefetch as in the SICOM paper last year. Essentially they use this disk cache to store movies for other peers to use. So the algorithm basically is a cache, replacement algorithm. The peer would be watching, the user would be watching some movie, and then after the viewing, that you have to, you can just decide to store that movie, but after a while, the cache will fill up. Okay, 1 gigabyte. Each movie, if it's 1 or 2 hours, it's probably at the resolution they are providing is about, I think, 200 megabytes around in that neighborhood. So 1 gigabyte you can store 4 or 5 movies if it's full length. Okay, so if you are storing just a fraction, then you can store more. So the question is which movies you keep in your cache. Okay, so you can use traditional cache management algorithms such as least recently used or least frequently used, and you can use this kind of algorithm. But in the system they built, they did a lot of experimentation, and they found out that this weight-based approach is better than the traditional one. Okay, the weighting factor is based on these two factors. One is how complete the movie is. Okay, so if some users may be just browsing, just watching part of the movie and then go away. So this is not so useful. If you watched almost the entire movie, this is more useful. So depending on how the fraction of a movie you have, that's one factor. Okay. The other factor is this availability to demand ratio. This is something that the tracker would collect from all the peers, what movie they are watching and how many peers are storing that movie. So they compute the ratio, and you can get this information from the tracker before you make the decision. And so these two things multiplied together is the weight. Okay, but all the movies, you essentially look at this weight and then decide which one to throw away. So once you start throwing away a movie, you just throw away the whole thing. You don't try to keep partial movies. So that's the algorithm. The third algorithm, I think, is very important in their system. Is I think in many systems, P2P streaming or P2P VOD, is the transmission strategy. This is, you are trying to get a chunk or a piece that many other peers have, and then you can ask any one of them, or can simultaneously ask multiple of them to get this. And so how do you do this? And I think this algorithm is again, this is, in their case, they have a sort of ad hoc way of doing it. Is they tried, experiment many times, but I think this is something that actually I'm studying with my student, trying to model this more formally, as an algorithm. So the idea is, how you have all these peers out there. Each peer is receiving requests from many other peers. They can be overloaded. Okay, so you want to more or less use up all the peers uplink, right, to offload the server. So how do you schedule so that each peer want to, if they just go to one neighbor to get the content, it's very risky because that neighbor may be gone. And you have to wait a long time and time out, and then just waited a long time, you didn't get anything. Okay, so the strategy they're using, the algorithm they're using, is to simultaneously go to multiple peers. Okay, even for the same piece or chunk. Okay, you will be asking different peers for different sub pieces. They don't ask the same sub piece, different sub pieces, and then dynamically adjust. How much to ask each neighbor that you are constant, sort of requesting from. And this algorithm reminds me of, the kind of, in the past I've done some work in TCP congestion control, right? This is very similar to that. How do you adjust the window size and the timeout to essentially make good use of all the, a set of neighbors you identified. And the algorithm is more complicated than TCP congestion control because this is like working with multiple. It's not only with one destination. It's multiple destinations, and it's very challenging. Okay, so this is something we are actually actively working on to as a research problem.
Let me ask some question on this, basically.
Okay.
The transmission strategy.
Okay.
We talked from the receiving side, right?
Mm-hmm.
But from the sender,
Mm-hmm.
what is its strategy to accommodate different requests? I may have, let's say, 10 or 20 peers
That's
asking
true.
me for content.
That's
right?
true.
Should
That's
I just
true.
routing them or accommodate for
That's true.
priority? Or, do you consider, for example, ISP?
That's true.
strategy?
I understand. Unfortunately, with the PP Live system, I didn't get enough detail from their system. In fact, they have a patent on this. They were, at the time we were writing this paper, they were applying for the patent, so we didn't get to the detail. But as I'm studying this problem, I know the question you ask is very relevant because the server probably don't want to keep, the request from all the users because that would increase the delay he has. There are many variations to this. The server probably wants to keep only certain requests, okay? And then that will determine how the users will set the timeout and all kind of things. So this is a algorithm that's can be quite complicated in reality, and that's why it's quite interesting. Okay, so I know everyone building a P2P streaming system has to work on this, and this affects the real performance, the efficiency of the system, as well as the user perceived performance. Yeah.
And you mentioned about basically TCP congestion control protocol. I think that's a very great direction. Although I don't know anyone have solved that yet. Basically, how we can combine TCP congestion control algorithm into this framework.
Yeah, what you need is actually is a new genre of congestion control. This is something that I think by the time somebody worked out the exact model, this is going to be receive so much interest, and they probably surpass the TCP congestion control. Okay, so the next part I will talk about is look at some of their measurement data. In this area, we look at several things. User behavior, that is, how much the user view a movie and whether it moves around, how often the users come into the system, and these kind of things. Okay. The second part is about replication, how to measure supply and demand. So this I touched on earlier, so we'll go to a little bit, see some real data. The third part is how to measure user satisfaction. This is a very important problem. Okay. In fact, this is also a problem we are actively studying as a research problem. If you want to deliver a P2P VOD system or streaming system as a platform or as a content provider, you better care about user satisfaction. In fact, in IPTV world, people study this very seriously. They have a term called a QoE, okay, quality of experience, and the whole issue is how to measure some simple parameters and then predict user satisfaction, because you are just broadcasting some content. You don't know whether the users are happy or not, and you cannot afford to ask them one by one. And if they are unhappy, if you are the operator, you are in big trouble, because they are going to phone call and there's a lot of problems. So you want to have simple ways to predict and monitor how the whole system is doing. Okay, so we'll show some of the results in this area as well. And the last part is I show some results about what kind of uplink bandwidth users have, whether they are behind firewalls, some statistics. So the data that we got from PP Live to do this study is based on just traces. In each trace, you can think of it as if you have used the NS, it's some similar to that. You have essentially a sequence of records, right? Each record contains basically, this is a simplified version of the record. You have a user ID, unique ID of a user, identifying a user, and then a movie ID, identify which video the user is watching, and then you have a start time, an end time, and the start position. Okay, so each viewing record could be just viewing part of a movie, and then if you jump to another point in the movie, that's a new viewing record. Okay.
These logs are collected on the client side, I see, and then uploaded to the server?
These logs are collected, yes. There's some kind of a log server, okay, which is maybe the tracker or is doing that job or something, and then the client will periodically send heartbeat message to this. Okay, yeah, and collecting this kind of information, as I said, is also an interesting problem. How do you? I mean, you cannot afford to collect everything. You probably are doing some kind of sampling, and how do you design it so that you collect as much information correctly as possible? So that's another challenge. So this is so after we got some traces from them, we look at a bunch of movies, and here's just they all similar in some sense, and here are 3 typical movies, and you can see that they are there's maybe around between 1 to 2 hours long, and then they we show here how many chunks there are, and how many viewing records we collected, which shows, and we use the fact that if the viewing record starts from the beginning of the movie, that sort of identifies a unique viewer. Actually, the viewer, the ID can also identify the viewers, but I think in the beginning, in the first version of their software, they don't have the viewer ID, a unique viewer ID. Okay, so we have to rely on this sort of viewing position to identify the viewers. And you can see that the average number of jumps is not that high. Okay, it's just 1 or 2 or 3 jumps when people are viewing. And one thing that's very interesting is how much does the user view, and whether most of the time the user viewing the whole movie or they're doing a lot of browsing. So as you can see from this, they are actually, the amount of movie they view looks like the average is very low. It's just a few percent. But if you look at the distribution, what you find out is that a lot of times the users are, because of the VOD system, they're browsing. They look at the first few minutes of a movie, and if they're not interesting, they go to the next movie and so on. And so a lot of the viewing records are short, but there are significant people who actually finish viewing entire movie. For example, the movie 2 here, you can see that there are actually a few thousand users which sort of saw the entire movie, because there's a big jump at the at the particular point. Okay, here. So this figure shows whether there are specific points that people tend to jump to. Okay, so this one actually shows for most of these viewing records, people start from the beginning, which is here, significant. The starting points at the beginning, and then after that, there's no specific points in the movie that people tend to jump to. They are just a random jump to different points. So that's what this figure shows.
Interesting. The user interface doesn't really give you any kind of chaptering information, right? Like you get with the DVD menus. So honestly, you just have the slider bar.
Yeah. They're just using the slider bar. I think that's why there's no specific place they tend to jump to. If they're a chapter, maybe that's true. Yeah. If there's a.
So you could cause their behavior to jump to more predictable places by changing the UI in a way that they probably like.
That's true.
Anchoring point algorithm may become a little bit more interesting in your chaptering.
If you have chapter, right, exactly. In their system, at least I think there's no chapter.
Interesting experiment. I think trying to force anchoring point.
You have a question? Okay. Okay, so this one shows how long the peers tend to stay in the system. This is very important. If they tend to stay there longer, then they can help the server more. So we looked at several days of trace records, and it shows that the users, this is the distribution for each day, that users staying for greater than 2 hours or a few minutes, you have a combination more or less pretty flat. And then so I think the encouraging thing is that users tend to stay for 15 minutes or more, so that they can actually provide some help.
So this is the number of unique users, right? They
Right.
are already basically identified
Right.
users in the
Right.
system, I assume. And I think you have something like 300,000 users per day.
Right.
Okay.
Right. This is I think this data may be
Seems around Christmas time.
Christmas time. Right. So this is actually the data that was originally submitted to SIGCOMM, and later on we adjusted some of the numbers when we send in the final version, because they actually did some additional. Some of the data came after the paper was accepted. Yeah.
You mean the date, or it's basically scrubbing the this?
No. We had some data which say measured in May of 2008 or whatever. This for different things. Yeah, you'll see a table later on.
Higher basically table or something. Higher number of users or something.
No, I didn't get any new number of users data. I think this is probably quite typical. I don't know whether they are significantly higher now or not. That's more like marketing issue. Yeah. I don't have latest information on that.
I have basically, so look at this VOD, right?
Mm.
There's a significant number of users watch big part of the movie, but they don't finish.
Right.
How can we interpret this behavior? So, for example, you have, I think, at least 20 or 30% of the user watch something like from 15 to an hour. It's a significant part of the movie, but they don't finish watching the movie.
Right. I think it's interesting. I think for VOD system, maybe a lot of time people are just browsing. They are not. They just want to kill time. I mean, I'm just guessing. I don't know. They are just looking at some movies, not interested. They can easily go to the next one, and this may be typical behavior, or this may be just behavior in China. I don't know. This could be if you have better quality and better content, maybe you have different behavior. So this is the business of measuring user behavior is quite kind of dangerous, depending on what content you have there and what So
one thing I'm interested in, when you terminate the application, does it stop, or does it go and stay in the system as a service that hangs around and still serves other peers?
Oh, the user, right?
Actually terminate, or does it quietly go off and continue serving peers?
This part I don't know. I think this is like you can design your software to cause either one to happen. I think.
I think they actually quit.
Sorry?
I think they actually quit.
They actually quit.
The reason is I noticed a big performance difference.
Okay.
When this application is running versus is not running regarding other applications.
All right.
For example, you're doing web browsing.
So my question really had this is more, you have a stronger results here for user behavior if the fact is that when they quit, they actually quit, right?
Yeah.
And then if you quit, then it just sneakily goes off and still does stuff in the background, in which case...
No, I think in this case, the result I'm showing you is how long the user is staying in the system watching. I mean, because this is what is logged, okay? The time they actually hang around, which they may still be helping, I don't know that part. Okay. This is how much they are actually watching, and then you can make sure they help. Okay, so this is
not dead time.
Yeah.
And this is the VOD part.
All right, this is the VOD part.
Live part.
Yeah. And the other thing on the right is we can see that definitely there's rush hours in the day or prime time. There's a certain time of the day you have a lot more users than other time of the day. Okay, so this is again for the whole week, and you can see that I think for them it's like lunchtime. There's a lot of people, sort of, and then in the evening. Okay, and then there's not too much after midnight or something. So
Question.
Yeah.
What is the vertical axis? Is the number of simultaneous users, or
number of simultaneous users watching a particular movie. So these are just
the order of 200 to 250?
Yeah.
Okay. Yeah. And the total number of users is on the order of 300K. I think they have something like 100 channels, something like that, right?
Yeah. Okay. They have something like 100 or 200 movies, popular movies. I think they adjust that number. Sometimes they have 500 movies or whatever. By the way, I must admit that I haven't. I'm not an avid user of their system. I mean, I probably tried with my student watched it part of a movie once, but so I'm not too familiar with a lot of this real system myself.
This data is only available for the inside the company. For normal users beside and outside the PP Live company, you are not going to get this data because this is completely based on the server.
People try to crawl that data, right? I mean, I can recall a number of basically universities try to crawl this and get some basically study.
You can get something, but not accurate.
Not as accurate.
No.
Of course.
So I think this data is released from the company rather than your students doing that alone. That's impossible.
Oh yeah, definitely. This is given to us by PP Live. Yes. The other thing is the sort of measurement to help to do the replication job. Okay, so we can look at the movie level. What is the supply? How many users? How many peers have online peers? who are viewing some other movie, who are storing these 3 movies that we're interested in. So we can see that this is actually out of 200,000 users, you have several thousand users sometimes storing the movies that we are looking at. Sometimes between a few hundred. And then you look at which chunk.
Let me ask you a question.
Okay.
I mean, I assume the date is similar to the previous slide. I mean, you are studying.
Yeah. This is from the same data set. Yeah, the same traces.
I mean, I noticed some basic issue. For example, I mean, look at the 18th hour.
Mm-hmm.
From 18th hour to 19th hour, the number of users catching this movie increased by something like 5,000. You have something like 500,000 more users catching this movie.
Mm-hmm.
Supposedly, this should mean you should at least have 5,000 more users watching this movie. But if we look at the previous slide, I mean, the top is something like 300.
Okay.
How to, I mean, why is this discrepancy? Versus
I think
10?
I think this number must be dependent on the resolution. I mean, if you're looking at any particular.
I mean, if it's a lot dependent on resolution, means you have a lot of user comes and goes.
Right. I think that certainly a lot of users that are browsing, and then they could. So in this case, they could be storing just a small fraction of the movie. As long as they have one chunk of the movie, they are storing that. They show up in this figure.
You weren't allowed to store portions of the movie, discard portion, right?
Right. You could be storing just portion of the movie, and then as far as the tracker is concerned, you are storing the entire. You're storing the whole movie. Yeah. So the second figure shows you, which are the chunks that actually get stored. You can see that the first few minutes get stored a lot more, and however, the sufficient number of copies of all the chunks are there. I mean, essentially you get about 30% always covered of the peers storing that movie.
For example, movie 2 is a very popular movie, right? I mean, at least the number of users storing it is high.
Yeah.
I mean, after 71 chunk, you don't have any users storing that chunk.
Oh, this figure actually is because these movies are different length.
Oh,
so this movie is much shorter. So this is always get to the
Okay.
Yeah. Okay, so this one is called the availability to demand ratio. So this is computing the dividing the how many people are storing the movie, storing movie versus how many people are watching it. So this let's see, availability to demand. I'm not sure whether this demand to availability or availability to demand. Anyway, this is trying to capture the ratio of people watching the movie versus storing the movie. Okay.
All this study is on the basic storage side, basically whether I have cache any portion of the movie versus,
Right.
I mean, you're asking for that.
Right.
I thought in the peer-to-peer VOD systems, it's
Right.
bandwidth which is more important than storage. Right. For example, let's say if I allow the user to catch, instead of 0.5 to 1 gigabyte,
Mm-hmm.
I can catch something like 10 gigabyte. I think even today, I mean, when they catch basically 0.5 to 1 gigabyte, they can catch on average 5 movies. So I mean, the storage basically amount is not that small.
Mm-hmm.
You can store basically, I mean,
Yeah.
the storage isn't that expensive.
Right.
But I mean, a more important basically figure is basically how much bandwidth you are actually available to serve the client.
Well, I think the bandwidth part is similar to P2P streaming. I think that the new problem for P2P VOD is the storage. How can you manage the storage so that when you have a user coming in to watch a particular movie, at the same time there may not be other people watching the same movie, but you want to make sure that there are other people storing that same movie, that what these peers want to watch.
We can talk this offline.
Yeah.
I don't think the storage is
It's a big-
that critical.
Okay.
Basically,
Okay. So the next problem, as I said, is the measurement of the user satisfaction. And this is mainly measured in terms of this thing called fluency, which is the percentage of time you are actually viewing out of all the time, including time there's buffering and you're frozen and all this other time. The left figure shows how many. So this information is sent from every peer to the logging server at the end of the viewing. Okay, so the left figure shows how many reports you get. You can see that when there are more users, you get more reports, basically. And the right figure is the interesting one. Is what is the fluency you actually get? Okay, so you want to have them all around here. Then it's good. But you can see sufficiently users are happy, which is when you have between 0.9 to 1 fluency. Okay, so it's a high fluency. But also there's a big. I think all this kind of measurement is always bimodal. Okay, so you have a bunch of users which just have hard time starting even. They probably do a lot of buffering and so on, and then they just gave up. Okay, so that's why you have some users with very low fluency. And then you have the rest of the users, they are just, you should have, this kind of, increasing curve. So this is a very typical measurement of satisfaction.
You don't mean total time of the movie. Total time, you mean viewing time plus buffering and freezes.
Pardon?
When fluency is viewing time divided by total time.
Total time, right.
By total time, you don't mean the total time of the length of the movie, right? You mean
no, yeah.
Viewing time plus buffering plus speed.
Yeah, exactly. Yeah.
I think basically it says that, for example, 80% fluency ratio.
Right.
Meaning, during time, let's say you watch a 100-minute movie, 80% of the time you are viewing.
Yeah,
the other
rather than
20 minutes is
You're waiting. You're watching the commercial or something. They make you watch commercials sometimes when you're yes.
This actually is a pretty bad performance. Every.
Yeah.
Yeah, I would think the number of interruptions would be crucial too. If you got interrupted every 3 frames for 1 frame, that would be much worse than if there was a big gap at the beginning.
Right.
Somehow under the impression that if that's the case, some of its competitors doing better in the VOD case than this one.
I must say the performance is not that great, but I think probably passable. And I think this is again, this is just a snapshot of a performance at a particular point in their deployment. Okay, so this is, I think the idea of the paper is not just trying to sort of study exact benchmark their performance. It's more like describing the design issues and what are the important problems and what things to measure, how to measure them. These are the things that I'm trying to deliver here. Okay.
So this is the result, I assume, December timeframe result, right?
Yeah. Right. This is December timeframe.
Some like May timeframe result.
May timeframe. No, I don't think I have that. Right. This is just showing a typical, this may not be related to the other figures. This is just sort of another snapshot. They're looking at their server, how they are delivering during the day. What's their CPU time, sort of usage, memory usage, and what kind of things they're using for the server. So this is not that interesting. Now this may be interesting to you. Huh?
Question for this server, did that act as both the tracker and content provider? So,
no, I think they have different servers for tracker and different for providing the source.
So this is just a content provider server?
Yeah.
So that figure is actually interesting because it shows that the server is pretty much maxed out at about 70% utilization. If you're actually running a server, you don't want it to hit 70%. It's pretty much maxed out. Doing it at these 2 times, the 2 peaks that you see. Right, corresponding to maximum upload rate.
Yeah. whatever you can make out of this. Yeah. So this is the some new things collected after the paper was selected. I think one of the reviewers says, "Oh, why don't you show us some, sort of what are the typical, sort of uplink contributions from different peers and downlink and so on." So this was measured in May of 2008. Okay, so you can see a distribution of, what peers are contributing and how much server is contributing. In this one, it actually shows the server is doing very well. It's only 8% something. Okay, the peers there's a whole distribution of different kind of peer contribution, and so I think this is kind of interesting.
So the download rate of the peers, have a quite wide distribution, right? So the movie is something like 360 kilobits per second.
Right.
This movie, right?
Right.
And you have peers downloading. You have something like 10% of peer downloading above 600 kbps, twice the movie rate.
I don't know why is that. Sorry. Yeah, that's one I don't know.
Okay. Because that usually indicates.
But that's a very small. That's a very small percentage, right?
It's 10% of the peer.
Yeah. Yeah.
And if you look at 360 to 600, depending on how much of the peers are actually close to 360, you may have a lot of peers down.
Yeah, I think this one maybe should be broken down into more finer granularity. If it's close to 360, it could be that those peers they are seeing a lot of losses, or they just have to do a lot of retransmission or whatever. That's possible as well. So another issue is how to measure the server loading. So the way it turns out that they are defining this server loading is during the prime time. Okay, the prime time is defined by sort of looking at the time of day and the most busiest 2 or 3 hours. And then because if the system is not during prime time, you actually don't care so much. If the server is already deployed, if they use a higher percentage of server, it's okay. And during the prime time, you want to make sure the server is not, loaded too much. Okay, so that's how it's defined. As I mentioned earlier, that for P2P streaming, they told me that they can achieve very, very low server loading, maybe less than 1%. Okay, I forgot the exact number, but for P2P VOD, initially, when the paper was written, the server loading was 20 to 30%, and by this time, it's around 10%. Yes.
So we must have a lot of servers for a particular movie, right?
Yeah.
So are they geographically distributed, and do they dynamically recruit more servers if they see
that part I don't know. I don't know the details. I know they have probably placed servers in different ISP networks. They actually work with ISPs to decide where to put the servers. The ISP may even provide them, some place to put a server that has high bandwidth, uplink bandwidth, and these kind of things. Yeah.
To manage that, right? I suppose.
These are some information about the NAT traversal. This 80% of the nodes are behind NAT boxes, and mainly 3 kind of NAT boxes. They use something like the STUN protocol to measure that. So the concluding remarks, I think the main message is, as I said earlier already, that we're just trying to, this is a system paper. We're looking at, relatively large-scale P2P VOD deployment at this stage. Later on, we'll probably see more, even larger scale. And we look at the design rationales, the insights we get from the deployment in the PP Live case. We look at important research problems to study, and we discuss how to do measurement, what kind of metrics to measure, and how to measurement, both in terms of measuring the replication for the replication algorithm as well as for user satisfaction, and that's it. And I think,
Let me ask a question. about the tracker scalability.
Okay.
Actually, when I record on this system designs, it seems to me that, I mean, currently the system may have issues if you really want to put all VOD and movies onto the system. So what I mean is, I mean, this may be okay to handle, let's say, 100 to 500 popular movies. But let's say you convert the whole website into a VOD server. Then the number of movies may be pretty large.
Right.
And look at the current algorithms. They basically need to track each chunk. What are the peers holding this chunk, right?
No. The tracker is only, I think, responsible for giving peers, you know, if you come in, you want to watch a particular channel, a particular movie, which other peers have stored that movie, not at the chunk level.
So it's basically on the movie level, not
Yeah,
on the channel
yeah.
level.
The chunk level is probably just additional information. They're not keeping necessarily up to date.
Okay,
The chunk level is you use gossip.
okay,
Okay.
okay.
Yeah.
Okay.
The tracker is doing the movie
So
level.
the gossip is actually beyond pieces. It's basically on the chunk as well.
Right. Because you exchange the bitmap yeah.
I would think that a difficult to handle case, but nevertheless a common one, unless the UI rules it out, is people that watch a movie and fast forward. So they actually only want one frame out of every chunk, or you know.
Yeah, they don't have this feature. They don't support this yet. This may be difficult.
Okay,
Yeah.
well, that works.
They only allow you to jump to a particular point, but not fast forward. Yeah.
What question? I've heard some speculation that the PP Live system performs well because a lot of the bandwidth is subsidized by large open pipes. That is like people in universities, right? Having like
I think this is
large
true for all the P2P systems. I think especially if you are in China, there are a lot of the ADSL users. They don't have a lot of uplink bandwidth.
Whether the measurement study that you did could either supports or disproves this particular speculation. So far, I know it's speculation. No one's actually managed to actually quantify it.
So this one, I think you can see some.
If you look at this study, I mean, the number of this kind of big peers isn't that much.
Yep,
So the peers with upload, I mean,
6%.
About 50% having less than the playback rate, roughly.
I'm recording their.
This is not as
basically-
Okay, all right.
I'm recording their live streaming designs,
Mhm.
I mean, which they talked in their last year's SICOM workshop. They mentioned they do use basically those big peers,
Right.
university peers. And those peers' bandwidth is actually much higher than 1 megabit. It's almost like 100 megabit. On
So
those
the
orders.
interesting question is what happens when university network administrators decide that that's enough, I'm going to
Yeah,
turn it
yeah.
off.
I think for this, I mean,
Greater granularity of studies, or you need to inject those studies when the paper is written.
And also this differs when there's a firewall of negative files for this upload and downloading, because the firewall traversal or net traversal will require some state maintenance in the mailbox or a
Good thing
stencil.
is usually for the university network, which are those basically big pipeline network, they are just on the open internet. They don't have net and firewall traversal issues.
Well, in many cases they have. For my campus network, yes.
Okay. Well, I mean, but many of the universities don't have the issue.
so do you think we should still go through this part 2? That I can quickly,
Slide do you have?
maybe about 20 slides. I mean, it's more about modeling work we're doing, and some of the, I mean, probably some things you already know.
Yeah,
So-
we have something like 15 minutes.
15 minutes. I quickly flip through this. Okay, so I think there's also great academic interest in this P2P area. Okay, so the talk I just gave is more like building the system. So in the academic community, people are studying basically these two kind of questions. One is, what is the limit? I mean, in terms of theoretically you can do. Second question is sort of how to model the algorithms so you can achieve these limits. I think for people working in this field, the secret, you already know, which is, for this P2P to work, essentially you have to use multiple trees, okay, to distribute the information, and you can build these trees either using this tree-based method or sort of mesh, but essentially you provide multiple paths from the server to all the peers.
Just basically, before I continue, are you studying the issue like in live streaming versus VOD? I think this is more
streaming,
like
live streaming, yeah,
okay.
yeah. So this is different than when people were doing multicast. They are focusing on just the efficiency rather than the maximum throughput. The capacity limit, basically, you can, if you don't make these two assumptions, it's kind of complex problem because you have to study, how to pack different trees, given a physical network. But people typically make these two assumptions. One is what is called the uplink sharing problem. Okay, this was mentioned in Menglinger's thesis in 2005. Essentially, define this. You assume that the network is not the bottleneck, so only the uplink of the peers are the bottleneck, and then you can derive, and also you make a fluid assumption, which is to divide the content into as many small pieces as possible. And in the limit, you can derive this result, which says that you can the maximum throughput you can achieve is bounded. In fact, you can achieve this pretty much by this formula. Is the minimum of the server's uplink, or the total uplink, including the server, divided by number of receivers. So some other useful results in the theoretical limit case is you have a stochastic model of peer population, which is by the Chu and Srikan model in 2004 SIGCOMM. And then I just want to mention that we also did a work in ICMP 2006, sort of trying to study in the theoretical case, what is the trade-off between throughput versus fairness of contribution. You can see the different ways you can achieve different level of throughput. And I think the question of studying the theoretical capacity limit, I think there's already rich literature. But I think what is beginning to happen is more and more papers focus on studying modeling these algorithms, okay, of the system, because we see a lot of really successful deployments, such as in PP Live's case. And can we actually, sort of have more rigorous study of the algorithms? For example, basically all the algorithms people are studying are the mesh network case, which is probably more challenging case. The tree case is more predictable, so the algorithm tend to be simpler. And I think one important result is this question about push versus pull based algorithms. Okay, I think there's a nice paper on this topic by these three gentlemen, Sanhavi, Bruce Hayek, and Masulie. And they have a paper in Transaction of Information Theory. Essentially, they look at the pull type of algorithm versus push. And the important insight is that the push part is important in the beginning for the fresh chunks when they are sending out from the server, because it helps the distribution scalability of distribution. And when there's already a significant number of pieces out there in peers, then the pull method is better. So this paper actually is very nice discussing these issues. We also did a paper in ICMP 2007 modeling the streaming case. Okay, that the other paper was more in terms of file downloading, looking at the sort of the maximum throughput and the delay and so on. So we did a paper in ICMP 2007, created a model to compute the continuity. Okay, so the intuition we got from there is that intuitively you would think that the greedy algorithm, which is sequentially get everything from servers sequentially, is the right thing to do. But it turns out that if you want the system to scale, it's important to do the rarer first. Okay, this is modeled in the paper, and it turns out the insight from is very similar to the previous work, the paper I just mentioned, because rarer first essentially is very similar to push. It's if you every peer select when they're pooling, they select rarest first. It's like pushing the new pieces first. Okay, giving priority to the new pieces. And then the important result we have in this paper is we show that actually a mixed strategy is the best. Actually, if you use a mixed strategy, you can achieve the most from in both dimensions. So this is our model. You have n peers, and the server is doing the push, okay, to the different peers, and then after every time slot, essentially everything is like a sliding window shift over, and then you play back one piece. And then the assumption we make, of course, the simplifying assumption is that you have a set of peers which are viewing at the same time. They have the same playback buffer size and a bunch of assumptions. But if you take these assumptions, then you can essentially compute the continuity, which is the probability of having a particular piece at a time when you need to play back. Okay, and you can compute this for different piece selection algorithms. So this is showing the sliding window. Each peer's buffer is like a sliding window in each time slot. Each peer randomly select a neighbor and then get a piece. And which piece you get is the piece selection algorithm. And then you can compute this thing, which is the in each time slot the probability a particular piece is gotten from your neighbor, and then essentially the probability of buffer position i+1 is equal to the probability you have the content in buffer position I in the previous time slot plus the probability you get that piece in the current time slot. Okay, you can essentially through the model get each of this quantity, and you can then it becomes solving a difference equation to get the continuity, and then we can study using this method, study the greedy algorithm and the rarest first, and this illustrates which the greedy is getting the one that's closest to playback, and the rarest first getting the newest piece. And then you can set up the difference equation for each case, and it's the reason you get this difference equation is shown in some lemmas in the paper, and then we solve these equations. I won't go through the derivation, but and you can get this kind of numerical results to see the two piece selection strategies. And you can see that in this case, the rarest first is doing better. Okay, this focus on the probability pi when I equal to 40. Okay, which is the playback position. And then we show that we can set up the same thing for the mixed strategy, which is again reduced to a difference equation, and then you can study the mixed strategy. And after we publish the paper, we actually theoretically can prove that the mixed strategy is always better than both the greedy and the rarest first. The mix is basically just saying we use part of the buffer to use the rarest first, and the other part use the greedy. Okay, and this is a closer look at how these three strategies do given the period of time. Okay, you can see that. Well, it's not very clear, but the mixed is almost 1. Okay, and So one of the strategies in the mixed strategies, you have to decide how big a portion of the buffer to use for the rarest first versus the greedy, which is this parameter m. So how do you set this parameter? So you don't want to have to set this parameter. You want this parameter to adapt based on the population size, and then you can show that you can actually let it adapt by saying just pick any m in the middle, and then say let's try to make sure this PM can achieve some target probability, say 0.3. And by doing this, you can essentially, because the system is not very sensitive to what you pick for the target probability, and then you can adapt to the right m, okay, given when the population size change. So more recent work we are continuing along this line is to model the we made a lot of assumptions in that model, so we're trying to relax the assumptions for have different peers have unsynchronized playback. They are using different kind of startup algorithms. We want to model the startup algorithm, and also as well as the P selection. And so that's one area we're doing work. The second area I already mentioned, to come up with a model like the future generation congestion control for P2P, how to do this transmission scheduling. The third area we're working in is the ISP-friendly content distribution. So these are the three areas. So the concluding remark, I think I'm wrapping up just in time now. So I think there's still many algorithms and variations to study. So this area is still very fertile for researchers. And maybe there needs to be some kind of common simulation platform, like an NS that's suitable for P2P. We are actually thinking about doing something in this area as well, if there's enough students. This, as I said, this resource allocation problem is very interesting compared to the congestion control we've been studying a lot. So these are just some thoughts. Yeah.
Has anybody looked at sort of blurring the line between this and peer-to-peer file sharing, where I can sort of, say what it is that I expect to be watching, and the thing can be proactively doing that and trying to get ahead to avoid the stalls? It would seem like if I could do that, it would encourage. I mean, one of the benefits to the network is it would encourage people to leave these applications running whenever their machine is idle.
That's a very interesting question. Yeah, I think you are saying essentially maybe you don't need to study the streaming. I mean, you just do file sharing. Just download the file.
It seems like you need the on-demand stuff, but it seems like there's also the application of people that just want to download the whole movie.
Right.
And it seems like that by mixing the two, you might be better than you could do with either of the algorithms separately.
Yeah, that's interesting thought.
Basically, the thing is, what are the performance difference? And also requiring a big movie usually have different user scenarios. And you want the application to have idea of honoring the usage basically requirement to allow the user to be comfortable using the application. So my observation is this: for example, in China, actually the peer-to-peer application which consumes most amount of traffic is actually a file sharing application. A lot of things shared on that network is movies. Mm-hmm. So you can say, okay, majority of the users actually want to download a movie and watch. Mm-hmm. And then it's those peer-to-peer streaming applications, PP Live, PP Stream, UC. They all start as a live streaming platform. We shouldn't for live. It's basically streaming platform where they open up something like 400 to 800 channels, mm-hmm. and the user can watch each channel. And on each of the channel, usually you have something like 2 minute window. So the user doesn't actually watch at exactly the same time. differ a little bit in terms of the time they are watching this movie. The protocol used actually is very like a file sharing protocol with a sliding window. That's basically the live streaming. And more recently, I mean, they are starting to offer a video on demand service. That's a new service being offered.
Right, yeah, it was just seeming like if you put multiple services on the same server, that you might get some benefits like the file sharing could get a lot slower at peak video on demand times to balance your resources better.
I agree. The interesting is basically utility balance.
Right.
I mean, and I think the utility balance even today isn't working that well. I mean, meaning, for example, if we are actually using a live streaming service, probably all others your service will have a very poor quality. Simply because, I mean,
if you other things you're trying to do on the machine at the same time, absolutely.
It's basically sucking all your bandwidth away.
Right, but if you're about to go to dinner, you'd be happy to let it get ahead while you're gone.
Any other questions?
I want to go back to the PP Live replication strategy stuff. So, is there implementation of the replication strategy particular to the fact that you're streaming movies, which are kind of large content, as opposed to things like YouTube videos, which might be something like 30 seconds? Do you know to what degree it's dependent on the fact that the length of the movie, and also the issue of the fact that you need all the data for file replication, like file transfer, whereas movies, you don't really need all the data to be useful? Do you have any sense of how they're taking that into account?
Interesting. I think from the user behavior we see, right, a lot of the users were actually browsing. I mean, they were. So I think at least the browsing part is similar to short, the short movies, I would think. Right. In contrast to their system, I think if you want to do like a YouTube system, right? I think the challenge is more, there's so many videos, whereas in their system, you probably only have like a few hundred. I mean, that's very, very small. So it's so the design, I think, will require some quite different design for at least the tracker part. So maybe you would think about doing something like email or something that help you scale up how to discover all the things. That's a very important part. Other questions? Thank you. Very, very interesting question.